Alright, so now we're going to discuss what is known as Noether's theorem, which is a result which relates symmetries of the Hamiltonian with associated conservation laws. And as we'll see, it's like this is expressed in terms of this notion of momentum maps, which we discussed earlier. So, Noether's theorem. Alright, so let me just state the theorem somewhat informally. Right? So if you have a Hamiltonian, H, which is a map from the cotangent bundle T star Q to the rails, right, is invariant under the cotangent lifted action of a Lie group G on Q. Right? Then the associated momentum map to this symmetry so this associated momentum map is denoted J. It's a map from the cotangent bundle to the dual, the Lie algebra. Right? It's preserved by the Hamiltonian flow. Okay, so let's try to prove this. So in practice, what we're actually going to prove is that we're going to prove that this J sub C, right? We're going to prove that J C, which is a map from the dual, the cotangent bundle to the rails, right? Where C is an element of the Lie algebra, right, is preserved. Okay. So I'm going to show this. So I want to show, and if you recall, it's like this J C is related to J in the following way. So if you have J evaluated on a point in T star Q paired with an element of the Lie algebra, this is just J C evaluated at alpha Q. Okay, so so it's not, it's probably not too surprising, if you will, that if J C is preserved, it's like along flows of the Hamiltonian vector field, that this associated momentum map is preserved as well. Okay, so but it's just easier to think of it in terms of this Hamiltonian-like object. So, all right, so let's start with the hypothesis, which is that if it has a Hamiltonian which is invariant under the cotangent lifted action of the Lie group G on Q. So if you recall, right, what is special about J C was that the Hamiltonian vector field associated with this, right, evaluated again at alpha Q, was equal to the infinitesimal generator, C on T star Q, evaluated on alpha Q. Okay. So what that more or less says is that if you look at the orbit, it's like which goes through a point alpha Q, that this orbit is generated by this Hamiltonian vector field. Okay, so what does it then mean? It's like that the Hamiltonian is invariant under this cotangent lifted action, right? What it really means is that, d dt of the Hamiltonian evaluated along the vector field, the flow generated by this infinitesimal vector field, right? Okay, so let's write that this way. Okay, for any time, right, and for some initial z0, right, this is equal to 0. Okay, but this is the time derivative of the Hamiltonian along a vector field generated by x C, or xj C, right, because of this equality. All right, but this thing is related to the Poisson bracket involving H and J cos C. Okay, and this is something which we showed when we studied first integrals in Hamiltonian systems. Okay, so this thing is equal to H paired with J cos C. All right, so more or less is that, we showed that the bracket of one function with another function is the time derivative of this function evaluated along the solution curve of the Hamiltonian vector field generated by the second function. Okay, so that's basically what's happening. I'm looking at how H changes along the solution curve of the Hamiltonian vector field generated by J cos C. But this Hamiltonian vector field generated by J cos C is exactly this infinitesimal generator of the group action. So more or less what this is telling you is that H is constant along the group orbit, right? The cotangent lifted group orbit of G on Q, which exactly is what one means when we say that the Hamiltonian is invariant under the cotangent lifted action of a Lie group G on Q. All right, so this is a consequence of the Hamiltonian H being invariant sort of with respect to the sort of cotangent lifted action. Okay. All right. So that's the first observation. 0 is equal to the Poisson bracket of H and J cos C. Okay, but you also recall that the Poisson bracket is skew symmetric. So what that means, so the Poisson bracket is skew symmetric. Right? So this thing, the bracket of J and cos C, the bracket of H and J cos C vanishing means that the bracket of J cos C and H also vanishes. So this implies that the bracket of J cos C and H is also equal to 0. Okay, but this has a different interpretation now, right? So this bracket, what does that mean? So this is equal to the time derivative of J cos C evaluated along the solution flow of a Hamiltonian vector field generated by H. Okay, but this is of course saying that J cos C is an invariant of the Hamiltonian flow. Generated by H. Okay. All right. So that's basically what you need to prove, right? So J cos C is invariant along it's like the Hamiltonian flow, and then by this relationship between J cos C and J, it also follows that J, this momentum map, is an invariant or preserved by the Hamiltonian flow. So that's what is called Noether's theorem. It's a very nice result because, again, it allows you to relate symmetries of the Hamiltonian with associated conservation laws. And again, it's the idea that the momentum maps associated with a symmetry of the Hamiltonian is conserved along the flow of the Hamiltonian system. So let's stop here.